There we go. So the hydrated radius is the radius when we have all the water around it compared to sodium or cesium here, which has only got 1 to 2 hydration number. And so these hydrated radii now are going to be similar because it takes into account both the ion size and all the waters associated with it. And there's more waters associated with lithium because it has this high charge density. Sodium's got a low charge density, so it's got less waters associated with it. Yeah, so that's what it says on the previous slide. Does that make sense on hydrated radii? Yeah? Okay. So if I say something like the charge density for sodium is higher than the charge density for potassium, which ion carries more water? You'll be able to tell me which ion has more. Now, it's hard to predict exactly what the hydrated radius is, but sodium here, we know sodium's a little bit smaller than potassium. Sodium has a hydration number of 4 to 5 water molecules per ion. Potassium has a hydration number of 3 to 4, so there's less waters around potassium because the charge density is lower. You guys good with that? Yeah? I see some heads nodding. Yeah?
Just a conceptual question. Are like the water molecules kind of neutralize the charge?
Yeah, exactly right. So there's, water, so there's other waters around here, right? Whoops. So the waters are just trying to neutralize the charge. The water's not going to react with the lithium cation, right? Because you can dissolve lithium chloride. Water doesn't react with sodium chloride when you dissolve it. It just hydrates it. So it separates those ions. So yeah, it's basically neutralizing the charge. So instead of sodium chloride, sodium chloride crystal is held together because you have Na plus and Cl minus, right? And so you have charge neutralization in this crystal because there's another negative charge right next to a positive charge, etc., etc. When you put that into water, it's not that the water reacts with these ions, but the water stabilizes the charges around the sodium and chloride, and that's why they dissolve. Does everyone get that? So it's interesting because, of course, when you take sodium chloride and put it in water, the water heats up. So we're used to talking about the heat of reaction, right? Bonds being broken and bonds being formed. But there's also something called a heat of solvation, which we'll talk about in the thermodynamics unit that we're going to start next week. And so it's a different type of interaction than oxidation reactions and stuff like that. So something to think about for the future. Was that my camera or someone else? Oh, okay.
My bad.
My camera's still working? Okay. Yes?
What's the relationship between Gibbs free energy and self-energy or Born energy? Because they seem to be very similar.
So, it's right here. Sorry. So, let's start with the Born energy. Okay. So the Born energy has this equation right here. Is this delta W, or this change in energy is related to this equation right here. And this is a differential equation, right? Because it's delta W and delta Q. So for every quanta of Q, you get a quanta of W. Now if you integrate W as a function, or with respect to Q, you get this mu I, or this chemical potential. So I show you the differential equation right here, and then or the delta, I guess this is the delta form of the equation, and then I show you the integral in this next page. And when you integrate this equation, you get this mu I, and this mu I is chemical potential. So it's got a different symbol when you integrate delta W with respect to dq. Now, if you take mu I and multiply it times Avogadro's number, you get delta G, or a form of the free energy. So the Born energy and the free energy are related to one another just by Avogadro's number. And so those are details, but what you really need to know most of all is what the sign of delta G is going to do. So why does the sign of delta G matter? Why might the magnitude matter? And at least in this case, how the Born energy is related to these two dielectric constants when you transfer an ion around in dielectric constant into different dielectric constant media. Because if you try and transfer an ion from medium 1 to medium 2 versus transferring that thing from medium 2 to medium 1, you're going to change the sign. So whether you're going from vacuum, 1 over 1, to water, 1 over 78, or from water to vacuum, you're going to get a different sign of this delta G, and that's really going to affect the thermodynamic favorability of the process, right? So these details are all fine and good, but the thing that we've talked about most is delta G and how solubility is related to dielectric constants. So that's probably the take-home message of this part. You know, I haven't asked you to crank out a bunch of Born energy calculations on the homework or anything like that, but I have asked you about solubility, hydration number. We've talked a lot about how dielectric constant is related to polarizability and solubility, so those are the things that I want to drive home. Does that cover it? Yeah? Uh-huh.
How does the strength of ion dipole interactions compare to other intermolecular forces?
Yeah, so that's a good question. So we have where are they? So we have an equation. It turns out that you can compute this intermolecular interaction exactly, right? So on the ion dipole interaction slide, we know this is the symbol for van der Waals energy, right? And we know that the van der Waals energy goes as the cosine of the angle between the dipole and the ion. That's very cool, very interesting. And it's got a form with distance of 1 over r squared, right? So energy is proportional to 1 over r squared in this. Now if we look at ion-ion interactions, which we also call Coulombic interactions, right? We know that the energy of Coulombic interactions goes as 1 over r. We know that the force, and this is where I goofed up on some people's homework, the force is 1 over r squared. But the energy of these Coulombic interactions goes as 1 over r. And so if we know the exact situation, we can compare these energies exactly. And that's what we do in the table, right? So if we have this table, which I don't have on here, but we can sum up, let me jump over to this thing. Lecture 3. There we go. So between orientational and you notice these are energies as a function of distance as well. And these are 1 over r to the 6th, right? So we've got our orientational interactions, our dispersion interactions, and our induced interactions right here. So if we have all the numbers, we can actually compute which is stronger, right? And that we can also see that from the table, right? Which interactions are stronger. And so when we try and compare ion-ion versus ion dipole, it turns out that we need to know the exact situation because they're both 1 over r squared. So we have 1 over r squared, or 1 over r, well, no, it turns out that we don't. So 1 over r interactions, this is a good one. This is a great question. I might make this a test question, as a matter of fact, because this is good. Okay. Coulombic interactions are ion, right? And the form of this is 1 over R. Okay? Ion dipole interaction, the form is 1 over R squared, right? When we look at lecture 4, slide, because the people at home can't see the screen. Lecture 4, slide 21, the energy or the van der Waals energy between ion dipole interactions is 1 over R squared. And we know that orientation, dispersion, and induced are 1 over R to the 6th. So if we have two things that are R equals 3, which interaction is going to be the strongest? All other things being equal. Coulombic, right? Because this is 1 over R squared, so as this number goes up, our energy is going to go down versus 1 over R to the 6th. And so we can say that Coulombic interactions are the strongest, all other things considered. Ion dipole interactions are somewhere in the middle because the form is 1 over R squared. And these orientational, dispersion, and induced interactions are 1 over R to the 6th. Now it depends. There's other constants in there. There's an angle in there. There's charges in there. So, there can be situations where perhaps ion-dipole interactions are stronger than ion-ion interactions. But in general, this is the order. Yeah?
Like, hypothetically, you did make that a test question. Would you give us the equations for each interaction, or were you expected to know that,
No, I will give you any equations that you need. I'll have an equation sheet on the exam. I'll give them to you. So if I ask you, But if I ask you something like, which interactions are strongest? Coulombic interactions or dispersion interactions, you should be able to know off the top of your head that Coulombic are strongest. But if I ask you for details of the equation, compute X,